The moon does not orbit the center of the Earth. Earth and moon both swing around a shared point, and that point sits inside the Earth, closer to the surface than to the center. That point is the center of mass. We build these three ways as a weighted average of two particles, as a sum over many particles, and as an integral over a continuous body. Then we locate it for the Earth and the Moon, and for a rod, first uniform, then with a density that changes along its length. Start with the simplest system, 2 point-like particles of masses m1 and m2. Pick an origin and let the position vector r1 point out to the first particle, r2 to the second. The center of mass is the vector r sub cm, defined as m1r1 plus m2r2, all divided by m1 plus m2. Read that as a weighted average. Each position is weighted by its own mass, and the total mass in the denominator normalizes the weights. Two checks make the meaning concrete. Set the masses equal, both to m. The numerator becomes m times the quantity r1 plus r2. The denominator becomes 2m. The m cancels, and we are left with the midpoint. Now let m2 shrink towards 0. The numerator collapses to m1r1, the denominator to m1, and the center of mass slides onto the heavy particle. So it is pulled toward mass, not toward geometry. And notice what it is, a point in space. Nothing has to be sitting there. Two particles generalize immediately. Take n particles labeled I equals 1 through n. The total mass of the system, written m sub cis, is the sum of the individual masses m sub I. The center of mass is 1 over m sub cis, times the sum of m sub I r sub I, same structure. Mass times position summed, divided by total mass. It is a vector equation, so it holds separately in each direction, component by component. Now push the particle count up. A solid body is not a handful of particles, it is a continuum. Chop it into infinitesimal pieces, each carrying mass dm and sitting at position r prime. The sum becomes an integral over the body. The center of mass equals the integral of r prime dm divided by the integral of dm. That bottom integral is just the total mass. The subtlety is that the integration variable is mass, not length. To evaluate it, you must trade dm for something you can integrate over space, and that is the job of the linear mass density. Locate the center of mass of the Earth-Moon system. The mean distance from the center of the Earth to the center of the Moon is 3.84 times 10 to the 8th meters. The mass of the Earth is 5.98 times 10 to the 24th kilograms. The mass of the Moon 7.34 times 10 to the 22nd kilograms. The Earth's mean radius is 6.37 times 10 to the 6 meters. The Moon's 1.74 times 10 to the 6 meters. The question is where the center of mass lies and whether it falls inside or outside the Earth's radius. Two particles, so start from the two-body definition. 1 over the sum of the masses times the quantity mass of Earth times r sub e plus mass of Moon times r sub m. Now the setup move that makes the problem easy. We can put the origin anywhere, so put it at the center of the Earth with the unit vector I hat pointing toward the Moon. That choice kills an entire term. R sub e becomes the zero vector, so mass of Earth times r sub e contributes nothing. What survives is the mass of the Moon times the Earth-Moon separation over the total mass along I hat. Substitute. The numerator is 7.34 times 10 to the 22nd kilograms times 3.84 times 10 to the 8th meters, which is 2.82 times 10 to the 31st kilogram meters. The denominator is 5.98 times 10 to the 24th plus 7.34 times 10 to the 22nd, or 6.05 times 10 to the 24th kilograms. Notice how little the Moon adds, barely more than 1%. Divide, and the center of mass sits 4.66 times 10 to the 6 meters from the center of the Earth. Compare that with the Earth's mean radius, 6.37 times 10 to the 6 meters. The center of mass is the smaller distance, so it lies inside the Earth, roughly 3/4 of the way out from the center toward the surface. The Earth does not sit still while the Moon goes around it. Both bodies circle this very point. Now a continuous body, a thin rod of length L and mass m uniform, its mass spread evenly. Find the center of mass measured from the left end. Set up coordinates first. Lay the rod along the x-axis with the origin at its left end, so it runs from 0 to L. Then build the mass element. Take a sliver of the rod, a distance x prime from the origin, of length dx prime. Because the rod is uniform, its linear mass density, mass per unit length, is a constant lambda equal to m over L. So the sliver's mass is dm equals lambda dx prime. That is the trait we needed. Mass expressed through position. The position vector of the sliver, r prime, is x prime in the I hat direction. Now integrate. The center of mass is 1 over m times the integral over the body of r prime dm, which is 1 over m times the integral from x prime equals 0 to x prime equals L of x prime lambda dx prime. Lambda is constant, so pull it out and use lambda over m equals 1 over L. That leaves 1 over L times the integral of x prime dx prime from 0 to L. The antiderivative of x prime is x prime squared over 2. Evaluated between 0 and L, we get L squared minus 0 all over 2L, which is L over 2. The center of mass of a uniform rod is at its midpoint, exactly what intuition predicted. That is the point of doing it. The integral machinery has to reproduce the easy case before you trust it on the hard one. Same rod, same length L, same total mass m, but the mass is no longer spread evenly. The linear mass density grows with distance from the left end, as lambda of x prime equals lambda 0 over L squared times x prime squared, where lambda 0 is a constant in kilograms per meter. The rod carries almost no mass near the left end and packs its mass toward the right. Two things to find, lambda 0 and the center of mass. Lambda 0 is fixed by the total mass because integrating the density along the whole rod must return m. So m equals the integral from x prime equals 0 to x prime equals L of lambda of x prime dx prime, which is lambda 0 over L squared, times the integral of x prime squared dx prime. The antiderivative of x prime squared is x prime cubed over 3, giving lambda 0 over 3L squared, times L cubed minus 0, which simplifies to lambda 0L over 3. Set that equal to m and solve. Lambda 0 equals 3m over L. Check the units, mass over length, kilograms per meter, exactly as promised. Now the center of mass, the same integral as before with the new density. It is 1 over m times the integral of x prime times the lambda of x prime dx prime. 1 over m is 3 over lambda 0 L, and the lambda of x prime brings in lambda 0 over L squared times x prime squared. The lambda 0 cancels, and x prime times x prime squared gives x prime cubed. The whole thing collapses to 3 over L cubed times the integral of x prime cubed dx prime from 0 to L. That antiderivative is x prime to the 4th over 4, so we get 3 over 4L cubed times L to the 4th minus 0, which is 3L over 4. The center of mass sits 3/4 of the way along the rod, not halfway. Piling mass toward the right end dragged the balance point from L over 2 out to 3L over 4. The definition never changed. Only the density function inside the integral did. That is the whole method. Choose coordinates, write dm as a density times a length element, and integrate. 3 forms, 1 idea. For 2 particles, the center of mass is m1, r1 plus m2, r2, over the total mass. For m particles, 1 over the system mass times the sum of m sub I r sub I. For a continuous body, that sum becomes the integral of r prime dm over the integral of dm. Every version is the same mass-weighted average of position. The Earth-Moon center of mass falls inside the Earth because the Earth outweighs the Moon by more than 80 times. The uniform rod balances at its midpoint. The rod whose density grows as the square of distance balances 3/4 of the way along change how mass is distributed and the balance point moves. The definition does not. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.